Discussion of today's topic is very important in the sense that we need to find out the critical speed of the rotor. In the previous videos, we have seen for the derivation part for damped and undamped condition of the rotor for rigid bearing support as well as flexible bearing supports. So now we have to find out the critical speed using some methods like Dunkerley methods, Rayleigh methods, and Jeffcott methods. But please understand that we need to calculate only the first critical speed using the above method. That means if you use the Dunkerley method, we can calculate only the first critical speed. Similarly for Rayleigh methods and Jeffcott methods. For higher modes of critical speed, we need to, there are various methods are available. However, I will discuss about generalized methods in the next videos. So let's discuss for all three method, that is Dunkerley methods, Rayleigh methods, and Jeffcott methods. Dunkerley methods is one of the methods through which the first critical speed is calculated, as we have seen, as we have stated. The critical speed calculated using this method is underestimated value of critical speed. That means the critical speed calculated by Dunkerley method is lesser than the actual critical speed. And how this is being done? So these are the methodology. Each load is considered separately and shaft stiffness is calculated based on the each load separately. So this is one point. Then the shaft diameter is considered uniform for the whole length. So if the shaft diameter of different value, then we have to take the average to be uniform whole for the whole length. Then natural frequency due to the each load and each shaft stiffness is to be calculated. And the natural frequency is calculated for each load using this formula. Let's say W is equal to a square root of K upon M in radian per second, where let's say W1, W2, W3, etc. are the natural frequency for each load considered separately. Then the Dunkerley methods, using Dunkerley methods, we can find W is equal to a square root of whole square root of 1 upon bracket start 1 upon W1 square plus 1 upon W2 square plus 1 upon W3 square and so on, bracket close. So this will give the radian per second. So this, using these methods, we can calculate this. So once this is done, we can calculate in frequency, natural frequency is Wf is equal to W upon 2 pi, which will give you, it will give you the hertz. And for the RPM point of view, if you want to find out the critical speed in RPM, you have to multiply with 60. So F is equal to F into 60 is RPM, critical speed in RPM. Little bit about how some standards formulas are available to find out the stiffness, shaft stiffness. So for the uniformly distributed load, just like shaft mass load, shaft stiffness is calculated using K is equal to 348 EI upon 5 L cube. Similarly, if point load is at shaft center, then shaft stiffness is 48 EI upon L cube. And if the point mass load between shaft end and shaft center in any side, then shaft stiffness K is equal to 48 EI upon bracket start LS into bracket start 3 times L square minus 4 times LS square bracket close. And if you want to calculate the mass of the shaft, you can use this formula. M is equal to RDS into pi by 4 into d square into L. So what are these above? K is the shaft stiffness due to individual load separately. Unit is Newton per meter. E is a Young modulus of elasticity in Pascal. I is a area moment of inertia of shaft, can be written as pi by 64 d to the power 4 m to the unit will be m to the power 4. A small d is average diameter of shaft in meter. L is the total length of shaft between the bearings, and ls is the distance between the load and the shaft end, in which side the load is located. So this will ensure that the value of ls is always less than L by 2. So if it is on the left hand side, so we have to measure from the left hand side. If it is on right hand side, we have to measure on the right hand side. M is the mass of shaft in kg, and RDS is density of shaft of material, that is kg per meter cube. Now let us understand how we can use the Dunkerley method with an example. Refer the picture above. A rotor has a point mass of M of 500 kg, that capital M is 500 kg, located at the center of the shaft, and mass M1 and M2 of, that is M1 is 100 kg and M2 is 80 kg respectively, located at a location of L1 is 1.5 and L2 we measure from right hand side is 1.8 respectively from the respective shaft end. The total length of shaft between the bearing is 6 meter, that is L is 6 meter, and its uniform diameter of 0.10 meter, and shaft material has Young modulus. Shaft material has a Young modulus of elasticity, this, that is 2.1 into 10 to the power 11 Pascal, and density is 7.8 into 10 to the power 3 kg per meter cube. Calculate the first critical speed. So now these are the example. We need to find out first critical speed using Dunkerley method. So shaft length between the bearing L is 6 meter, diameter of shaft is 0.10 meter, area moment of inertia of shaft I is equal to, using this formula, 4.91 10 to the power minus 6 m to the power 4. Young modulus of elasticity is 2.1 into 10 to the power 11 Pascal, and density of shaft RDS is 7.85 into 10 to the power 3 kg per meter cube. So now point number 1, natural frequency due to only shaft mass. So mass of shaft is calculated, m is equal to RDS into pi by 4 d square into L. So m is 369.9 kg. In formally distributed load, so you can find out shaft stiffness K1 348 EI upon 5 L cube. So K1 will be 3.67 10 to the power 5 Newton per meter. So natural frequency due to only shaft mass, W1 is equal to square root of Q1 upon M, and which is W1 is 31 radian per second. Now point number 2, natural frequency due to only point mass capital M at center. So point mass M is 500 kg, and point mass load at center. So shaft stiffness K2 will equal to 48 EI upon L cube. So K2 will be 2.29 10 to the 5 Newton per meter. Natural frequency due to only point mass capital M, W2 is coming as 21 radian per second. Now point number 3, natural frequency due to only point mass M1. So mass of point load M1 is 100 kg, distance between load and shaft, that is left hand side, L1 is 1.5 meter. So point mass M1 stiffness K3 can be written as 48 EI upon bracket start L1 into bracket start 3L square minus 4L1 square bracket close. So K3 is a 3.33 10 to the 5 10 to the power 5 Newton per meter. So natural frequency due to only point mass M1 omega 3 is 58 radian per second. Now point number 4, natural frequency due to only point mass m2. Similarly, mass of point load m2 is 80 kg. Distance between load and shaft end, that is on right hand side, L2 is 1.8. So shaft stiffness K4 is equal to 48 EI upon bracket start L square into bracket start 3 L square minus 4 LQ L square bracket close. Bracket start 3 into bracket start 48 EI upon bracket start L2 into bracket start 3 L square minus 4 L2 square bracket close. So K4 is 2.89 into 10 power 5 Newton per meter. So natural frequency due to only point mass M2, W4 is coming 60 radian per second. So now we have to calculate using the Dunkerley methods. So natural frequency W is equal to square root of 1 upon bracket start 1 upon W square W1 square plus 1 upon W2 square plus 1 upon W3 square plus 1 upon W4 square bracket close. So W is coming 16.05 radian per second. So natural frequency in Hertz is 2.55 and first critical speed in RPM is F into 60, which is 153 RPM. So this is the way we can calculate the first critical speed using the Dunkerley methods. Now we have to use Rayleigh methods. Rayleigh method is one of the methods through which only the first critical speed is calculated, and critical speed calculated using this method is overestimated. That means the critical speed calculated using the Rayleigh method, its value is more than the actual critical speed, and each load is considered separately and shaft stiffness is similarly calculated separately. Shaft diameter is considered informed. That means if there is a variation of the shaft diameter, we have to take the average. Deflection due to each load is to be calculated separately, considering only one load at a time. And deflection due to only one load can be calculated using the formula Y is equal to M into G upon K. So Y is a deflection in meter, M is a load in kg, K is a shaft stiffness due to load only, Newton per meter, and G is acceleration due to gravity, 9.81 meter per second square. So this is through which we can calculate the deflection due to each load separately. Then Rayleigh method, using Rayleigh methods, natural frequency of rotor W is equal to square root of K1 Y1 square plus K2 Y2 square plus K3 Y3 square plus K4 Y4 square dot bracket close upon bracket start M1 Y1 square plus M2 Y2 square plus M3 Y3 square plus M4 Y4 square dot bracket close. So this will give the natural frequency in radian per second. So where K1, K1, K2, K3, K4, etc. are shaft stiffness due to each load considered separately in Newton meter per meter. Y1, Y2, Y3, Y4 are deflection due to each load considered separately in meter. And M1, M2, M3 are the load considered separately in kg. So first mode natural frequency will be W upon 2 pi in hertz, and first critical speed will be F into 60 in RPM. So this is the way we can calculate critical speed using Rayleigh method. Now let us same way in how this is the same thing. Informally distributed load shaft stiffness K is 348 EI upon 5 LQ. Point load at shaft center shaft stiffness K is 48 EI upon LQ, and point mass load between shaft end and shaft center in any side is K is equal to 48 EI upon bracket start LS into bracket start 3 LQ L3 L square minus 4 3 L square minus 4 LS square bracket close. Mass of shaft M is equal to RDS into pi by 4 ds square into L, where K is a shaft system, E is Young modulus of elasticity, I is the area moment of inertia, pi by 4 d to the power 4, Small d is average diameter of shaft, L is the length of shaft, LS is the distance between the load and the shaft end, and M is the mass of shaft, RD is the density of shaft material. Now let us understand using an example how to calculate critical speed using relay methods. Refer picture above. A load has point mass of 500 kg at center of shaft. M1, M2 are 100 kg, 100 kg and 80 kg respectively, located at location of L1 is 1.5 and L2 is 1.8 meter respectively from the respective shaft end. Total length of shaft between the bearing L is 6 meter and it is informed diameter of 0.1 meter. Shaft material has Young modulus of elasticity 2.1 into 10 power 11 Pascal and density is 7.85 into 10 power 3 kg per meter cube. Calculate first critical speed. So solution: length of shaft between the bearing L is 6, diameter of shaft small d is 0.1 meter, area moment of inertia of shaft I is after putting the value it is coming 4.91 10 to the power minus 6 meter, m to the power 4, Young modulus of elasticity is 2.1 into 10 to the power 11 Pascal, density of shaft RDS is 7.85 into 10 to the power 3 kg per meter cube. Now first point, stiffness and deflection due to only shaft mass. Mass of shaft M is calculated RDS pi by 4 d square into L. After putting this value it is coming 369.9 kg. Uniformly distributed load shaft stiffness K1 is equal to 348 EI upon 5 L cube. So K1 is 3.67 into 10 power 5 Newton per meter. Deflection due to only mass shaft Y1 is equal to mg upon K1. So Y1 is 9.9 into 10 power minus 3 into sorry yes y1 is equal to, after putting this value it is coming 9.9 into 10 power minus 3 meter. Now stiffness of the and deflection due to point mass m at center. Mass of point mass m capital M is 500 kg. Point mass load at shaft center. So then shaft stiffness K2 is equal to 48 EI upon LQ. So K2 is, after putting this value, it's coming 2.29 10 to the 5 Newton per meter. Deflection due to only point mass M2 is equal to mg upon K2. So Y2 is equal to 2.1 4 into 10 to the power minus 2 meter. Now stiffness and deflection due to only point mass M1. Mass of load M is 100 kg. Distance between shaft L1 is 1.5 meter. Shaft stiffness K1 is equal to 48 E upon bracket start L1 into 3 L square minus 4 L1 square bracket close. After putting all this value, K3 is equal to 3.33 10 to the power 5 Newton per meter. Deflection due to only point mass M1 is equal to, which is Y3 is equal to 2.94 10 to the power minus 3 meter. Now point number 4, if stiffness and deflection due to only point mass M2. So point mass M2 is 80 kg, distance between load and shaft is L2 is equal to 1.8. For point mass M2, shaft stiffness after putting all these values is coming as 2.89 10 to the power 5 Newton per meter, and deflection is coming at 2.7 10 to the power minus 3 meter. Now natural frequency of rotor, after putting all this value, it is coming at 23.38 radian per second. So first mode natural frequency in Hertz is 3.72 Hertz, and first mode or first critical speed is multiplying, after multiplying 60 with the F, it is coming to 3 RPM. Now Jeffcott method. So we have understood both Dunkerley and relay method. Now let us understand about Jeffcott method. Jeffcott method is considered when rotor is simply supported and bearing is considered rigid. So that is why it is written single mass consider at concentrated at center of the shaft and simply supported by rigid bearing. Mass of shaft is neglected. So mass of shaft is considered. Now it is transferred or converted, placed at half of its total mass at shaft's center span. So total mass is distributed and consider half of this mass at center. Then modal mass of shaft centrally mounted rotor is generally 0.55 to 0.65 of total rotor mass. That means if rotor mass is known, this can be considered is 0.55 to 0.65 modal mass. Average diameter of shaft is taken as shaft is to be considered uniformly diameter, and undamped critical speed omega CR is equal to square root of K1 upon modal mass, where K1 is a shaft stiffness in Newton per meter and modal mass in kg. If shaft damping C1 is a C1 is Newton second per meter, so standard damping C2 is equal to 2 into square root of K1 into modal mass, so 2 m omega CR, m is a modal mass. Shaft damping is E1 is equal to C1 upon C0 constant. So damped natural frequency omega dr is written as omega CR into square root of bracket start 1 minus E1 square bracket close in radian per second. So these are the steps through which we can calculate the critical speed using Jeffcott methods. For Jeffcott rotor, it is simply supported rotor and mass is at center. So let's say D is average diameter of shaft in meter, L is the length of shaft between bearings M meter, L, and L is the length of shaft between the bearings M in unit. A small m is a modal mass at center of shaft is kg. E is a Young modulus of elasticity of shaft in Pascal. Now area moment of inertia of shaft I is equal to pi by 64 into d to the power 4 will be can be written as m to the power 4. A stiffness of shaft due to modal mass given is equal to 48 EI upon L cube. First natural frequency is calculated omega or is a square root of or W is equal to square root of Q1 upon modal mass. First natural frequency in hertz is equal to W upon 2 pi, and first critical speed is equal to F into 60. So damped natural frequency will be omega dr is equal to or W dr is equal to omega CR into square root of 1 minus E1 square bracket close. So E1 is a shaft damping. So now let us understand through an example. Rotor has total mass of 450 kg is supported between the bearings having a span of 1.8 meter, shaft diameter 0.165 meter, and shaft material has Young modulus of elasticity of 2.1 into 10 per 11 Pascal. Shaft damping is 11,000 Newton second per meter. Calculate the undamped and damped first critical speed. So these are the refer the photo. Model mass of rotor M is 0. Let's say 0.55 into total mass, which is coming as 247.5 kg. Area moment of inertia of shaft I is equal to pi by 64 d to the power 4. So after putting all this value, it is coming 3.64 into 10 to the power minus 5 meter 4. Young modulus elasticity is 2.1 10 to the 11 Pascal. Length between the bearing L is 1.8, a stiffness of shaft 48 EI upon LQ. So K1 is equal to 6.29 into 10 to the power 7 Newton per meter. First undamped natural frequency WCR or omega CR, you can write square root of Q1 upon modal mass. So omega CR or WCR, which can be written as you can call omega CR or DS. WCR 504 into 1 radian per second. So undamped natural frequency F is equal to WCR upon 2 pi, which is 80.22 hertz, and undamped first critical speed in RPM is 4,813 RPM. Now shaft damping C1 is 11,000 Newton second per meter. Standard damping C0 is 2 into square root of K1 into M. which is nothing but 2 into m into omega CR, 2 into 247.5 into 504.1, which is coming as 2.5 10 to the 5 Newton second per meter. Shaft damping ratios, E is equal to E1 is equal to C1 upon C0, which is coming 0.044, and damp natural frequency WDR is equal to WCR into square root of 1 minus E2, sorry, not E2, E1 square. There is a wrong here. 1 minus E1 square. So after putting this value, omega WDR is equal to 504.1 into square root of, the square root is nothing but this is a square root. You can also write SQRT is a square root. 1 minus 0.004 to the square, which is coming at 503.6 radian per second. So damped natural frequency in hertz is 80.15, and first critical damped critical speed is equal to 4809 rpm. So thank you. I hope you have understood how the critical speed for the Dunkerley method or using Rayleigh's method or finally Jeffcott methods are used, and Dunkerley methods are underestimated. That means the value calculated through using the Dunkerley methods is less than actual critical speed. And similarly for the Rayleigh's methods, the value calculated using the Rayleigh's method is overestimated. That means it is more than the actual. And finally, we have also understood how to calculate the critical speed using the Jeffcott methods. So thank you for watching.